Welcome to Testiv's lesson on trigonometry for the ACT math test. My name is Carlos Cousins. I'm a Testiv coach, teacher, ACT college prep guru, and I'm here to help you through the process of studying for this section. So the trigonometry section. Overall, geometry and trig is the area where Testiv students see the highest increase, though it's questionable if you believe that trigonometry is the reason why geometry and trig, is the reason that people see the highest improvement. It turns out trig questions make about only 6% of the math test questions, and that's accurately reflected on test tips. So that's only 4 out of the 60 questions you'll see on the test. It's very few of the ones you'll do on the site. Uh, and we thought it'd be a good idea to provide you guys with a lesson that might help you prepare for this if you're, interested in getting your score as high as it can go in this section of the test. There are definitely skills you can learn that make these questions easy to tackle, but there's a lot of formulas. And when I'm speaking about a lot of formulas, it really depends on if you've taken trig before. A lot of this will be, material that you've already seen. If you haven't, it'll be brand new and maybe a little bit daunting. So what is ACT trigonometry about? So the ACT trig is going to cover the unit circle, which we're going to talk about briefly in a second, Sohcahtoa, reciprocal identities, quotient identities, the Pythagorean identities, arc functions, graph transformations for sine, cosine, and tangent, and the law of sines and cosines. And these last ones are definitely the law of sines and cosines, something that's much rarer, but they do show up, and it's something that we want to talk about. Now, for those of you that have taken trig before, what is the ACT trig not about? So ACT trigonometry is not going to be about the cofunction identities, even odd, sum difference, sum to product, product to sum formulas, double angle or half angle formulas, or any of the longer formulas that you needed to know, any of the longer identities. Though these can help. And if you know this already, then you're in a really good position for scoring really high on this section of the test. Uh, well, it is only 4 questions, but okay. So what I want you guys to do is for the purpose of this lesson, just pull out a cheat sheet, just a random, 8.5 by 11 sheet of paper, so that you can log anything that you see on there that you don't know cold, anything that you don't know by memory, that might help you if you remembered for the test. So the unit circle, for those of you that are looking at this for the first time, or even if you look at it in the past, it's very daunting. It's got a lot of symbols, a lot of numbers, and it can be very easy to just get a little bit scared by what's being presented here. But what I want to show you today is it's actually really useful. Not necessarily to memorize everything on it, which is not what I advise, but just to know how it works and how it can help you solve some problems. So let's go ahead and try that together first. Um, Try and see if you can already answer these on your own. Go ahead and pause the video if you know how to do this already, and try to figure it out on your own. If you do not know how to do this, I'm going to be talking about that momentarily. What you need to be able to do is read this like it were a don't think about it in any other way. This is just a graph that's giving you useful information. What's going on here is the coordinates of the points along the circumference of the circle. So along, the like the perimeter, the circumference of the circle. What you see is you have these points here that are logged for you. And each of these has coordinates that are actually cosine, comma, sine. So if you think about, this is an xy coordinate plane, the x value is going to be a cosine, and the y value is going to be a sine. So each of these points has the values for x and y logged over here, and what they're telling you here is for what angles these are the coordinates. So 30 degrees is a measurement of this angle in degrees, so 30 degrees, and pi over 6 is a measurement of the same angle in what they call radians, which is just another version of how you can measure degrees. So knowing that, if they asked you for the sine of pi over 6, which we know is 30 degrees, you'd have to look at the 30-degree part here of the unit circle. And we see that the cosine is is plotted as square root of 3 over 2, and the sine as 1/2. And they're asking us for the sine of pi over 6, so the answer then is going to have to be 1/2. You can do the exact same thing for the cosine here. The cosine of 30 degrees, well, that's the same. 30 degrees is the same as pi over 6, like we just saw. They're labeled together. That's going to be square root of 3 over 2 because the cosine is in the place of x, in the plotted points along the circumference, so square root of 3 over 2. The next thing here is asking for the sine of 90 degrees. So you have to look at 90 degrees, that's this right angle here, and we see that 90 degrees corresponds to pi over 2, and we're told that the cosine of 90 degrees is 0, and that the sine of 90 degrees is 1, and we're being asked for the sine, so the sine of 90 degrees is just going to be 1. What is the cosine of 5 pi over 6? Again, you look for 5 pi over 6. It happens to be right over here. That's the same as 150 degrees. And we're asked for the cosine. So again, the cosine is negative square root of 3 over 2. And the sine is 1/2. So the answer here is negative square root of 3 over 2. Uh, Now, this last question is asking us for the sine. So what is the sine of 300 degrees? You go for 300 degrees or 5 pi over 3. And they're asking for what the sine is. So cosine is 1/2. Sine is, again, negative square root of 3 over 2. If you've studied this before, you would know this. If you do not, you should start to see that there's a pattern here. Um, and this is what should actually be really useful for, what you want to memorize. Don't try to learn the unit circle values by rote memorization. The pattern is what's going to be key here. If you know the values for, just the values of the numbers on this first quadrant here, quadrant being like one of the quarters of the circle. Um, so in the first one here, if you know that for 0, the cosine is 1 and the sine is 0. For 30, the cosine is square root of 3 over 2 and the sine is 1/2, etc., etc. All that you need to remember is how the values change from positive to negative or negative to positive. So if you go down here for the corresponding 30 degrees pi over 6, the corresponding side on this quadrant, that's 210 degrees, 7 pi over 6, negative 7, oh, sorry, 7 pi over 6. That gives you the same values, square root of 3 over 2 and 1/2, except now they're both going to be negative. You went from a side where both of them were positive to a side where both of them were negative. If you go from this to, for example, the equivalent on this side, which is 5 pi over 6, or 150 degrees, just the first one is going to be negative. The cosine value is going to be negative. And that's what we see here, negative, positive. And that way, if you remember what just what all the values are in this quadrant, you can really easily figure out the values of cosine or sine for any of these angles in any of the other quadrants. What really matters for you to memorize, if if you're trying to figure out how to score the highest score that you can get in this section, is the values for cosine and sine for these angles here, for 0, 30, 45, 60, and 90. Or, 0, pi over 6, pi over 4, pi over 3, and pi over 2. The other thing you need to know for this test is Sohcahtoa, and this is just a really, nice mnemonic to use. The S stands for sine, the C stands for cosine, and the T stands for tangent. And these words over here, these letters over here, the O and the H, the A and the H, and the O and the A, stand for the measurements of sides of a triangle, as you'll see. So is going to be sine of theta equals the opposite side. So in this case, let's say we're taking the sine of theta over here. The opposite side of theta is A. The opposite side to theta is A over the hypotenuse. And the hypotenuse is just the longest side of a triangle. Not one of the shorter legs, but the longest side. And in this case, this is the hypotenuse, side C. So the opposite over the hypotenuse, you get A over C. And you do the same here. So Sohcahtoa. Ka stands for cosine of theta equals adjacent over hypotenuse. So in this case, the adjacent is the one that's next to it, not opposite to it. So B over the hypotenuse, B over C. Toa, tangent equals opposite over adjacent this time. So we said the opposite was A and the adjacent was B, A over B. And this way, if you have values for A, B, and C, and you ask for the sine, the cosine, or the tangent of some number, so some angle value theta, you can easily solve for them by using these Sohcahtoa formulas. So for example, if you're asked a question like this on the test, in the right triangle ABC in the figure, if cosine of A equals 12 over 13, so the cosine of A is going to be 12 over 13. Cosine, we said, was that's cosine of adjacent over hypotenuse. The adjacent is going to be 12 The hypotenuse, which is the longest side, is going to be 13. Okay, and we're told that AB equals 12. Oh, well, we already knew that because of the cosine. Um, then the length of BC is what? Well, now this is just a Pythagorean theorem exercise, which you should know from your plane geometry lesson. So let's go ahead and take a look at that. So we know that a squared plus b squared equals c squared. So let's label this side b. Why not? We know that a squared is going to be 12 squared, which is 144, plus b squared, which we don't know just yet, is going to equal c squared, which is 13 squared, which is 169. So now you can just solve for b squared. Oh, that is a very ugly b. That was more a 6 somehow. Um, so b squared is going to equal 169 minus 144, which is 25. So b is going to have to equal 5. And that's how you would solve this type of problem. The other identities that you need to know are the reciprocal and the quotient. These sound very confusing. Reciprocal just means this. You need to know these formulas here. The sine of x is the same as 1 over this other function called the cosecant of x. So the cosecant of x would be 1 over the sine of x. Just something to remember. Write these down if you haven't seen them before. These are the identities that you'll need to use the most in ACT trig questions once you also combine them with the quotient identities. So the cosine of x is 1 over the secant of x. The tangent of x is 1 over the cotangent of x. And this quotient is that the tangent of x is also sine over x over cosine of x. That's a little bit different than anything we've seen before, but it's the only quotient identity that you need to know. And what's really cool now is if you think about your unit circle, the only things we were graphing on the circumference of the circle were cosine and sine, right? We weren't graphing any tangents. But if you were asked for a tangent value, well, what you can do is think to your circle and solve for what the sine of whatever, whatever the angle in question is over the cosine of that angle. And that there, just using the unit circle, you should have more than enough information to solve for what the tangent of the angle in question is. You just divide the sine divided by the cosine and you've got it. And this can be really useful for solving questions of this type. So this is just asking you the product of the sine of some symbol, times the cosine of that symbol times the tan of the symbol, or the secant of the symbol times the cotangent of the symbol is equivalent to what? Well, we know the cosine is the inverse of the secant, so these are going to cancel out, and the tangent is the inverse of the cotangent, so these are going to cancel out, and the only thing you're left with is the sine of that symbol, so it's a sine. And that's how you solve that problem. A more complicated one might look like this. So in this right triangle, tangent of theta is equal to which of the following? Well, we know tangent from Sohcahtoa is toa, right? Opposite over adjacent. So the opposite side of the tangent of theta is going to be A, and the adjacent side is going to be B. So it turns out that the tangent of theta is A over B, and that's one of our answer choices. But let's try the other ones. So uh, tangent of theta is the same as sine of theta over cosine of theta. Well, it turns out that this was actually our quotient identity. So if we go back, we see exactly that. Tangent of x equals sine of x over cosine of x. So this one has to be true as well. So already we can cross out anything that doesn't have 1 and 2. So, none of these make sense. Both of these. Okay, that is valid. This one only has 1, but it doesn't have 2, so that one isn't valid. This has to be the right answer choice. The other thing you need to know for this test are the Pythagorean identities. So what are these? These are usually formulas that they're going to be testing for directly. The one that most often comes up is this one: the sine squared of theta plus the cosine squared of theta is 1, or the sine squared of x plus the cosine squared of x is 1. But these two do show up once in a while. And they're just usually going to ask you to solve, maybe some algebraic equation, and you end up with a value that is, for example, 1 plus cotangent squared of theta. They're going to ask you what is the answer choice, and you're not going to see this answer choice. Instead, you're going to see this, and that's going to be the correct answer. So let's go ahead and look at a problem that kind of looks like that. So which of the following expressions below is equivalent to the cosecant squared of x? Well, we go back to our Pythagorean identities. We know that the cosecant squared of theta is 1 plus the cotangent squared of theta. So the cosecant squared of x is going to be 1 plus the cotangent squared of x, and this is the right answer choice. The other thing you need to know are arc functions, and this is important to keep in mind. The arc sine, or the sine, -1 of x, this is called the arc sine, there's no other way of calling it, is not the same as 1 over the sine of x. That's going to be expressed not like sine to the -1 power of x, which is the arc sine of x. It's going to be expressed as sine of x, like this, with a double, with a double parentheses, all of that to the -1. And that's going to be 1 over the sine of x, which like we saw earlier was the cosecant. The arc sine, however, is really cool because if you take the sine of the arc sine of some value, these cancel out and you end up with that value as the answer choice. So the sine of the arc sine of x is just x. The cosine of the arc cosine of x is just x. The tangent of the arc tangent of x is just x. So that's really useful for solving a whole series of problems. So let's go ahead and try one out here. So express the cosine of the arctangent of x without trigonometric functions. So this is really cool because we know that the cosine from the previous formulas we looked at was the same as 1 over the secant of x. Let's call this value here in between the parentheses y, just so that we don't get confused. So 1 over the secant of y. And why did I do that? So the reason I changed this up originally is because we want this expression expressed without trigonometric functions, and we were given an arctangent. So what I want to do is take the tangent of the arctangent to get rid of the arctangent and end up with the x alone in some way, uh, so that I no longer have to deal with trigonometric functions in the answer. So what we can do is try to now put cosine in terms of tangent. And 1 over the secant of y gets us halfway there, and that's because we looked at another formula earlier that told us something about secant squared. When we have the secant squared of theta, that equals tangent squared of theta plus 1. So if we have the secant alone, that's going to be the square root of tangent squared of theta plus 1. Or in this case, tangent squared of x plus 1. So what we can do is 1 over the square root of tangent squared of y, which we said was standing for arctangent of x, plus 1. What's really cool is now we can plug in the arctangent because we already have the tangent. So if we take the tangent of the arctangent, these cancel out and you end up with tangent square, it's tangent of y times tangent of y plus 1, which, if these are going to cancel out, is going to equal, 1 over x times x plus 1. And remember, the entire denominator we were taking the square root of, so this is going to be the answer choice, which happens to be answer choice B, and that's how you solve this problem. We'll see these can be really useful for all sorts of problems once you commit them to memory, and this is why I'm having you write them down in the cheat sheet. Uh, the other thing you need to know is actually quite easy. These are the graphs that you need to remember for sine, cosine, and tangent. And all that you need to know is that for the period of sine, so starting from the origin over to the second time that the graph crosses the x-axis, we have a typical graph function shape that looks like this. Sorry, a sine of x shape that looks like this. And then if you go from 2 pi onward, it'll just repeat. If you go backwards, it'll just repeat. But what really matters is that the figure that's repeating is this one. And from the origin, it'll go from 0 to pi and to 2 pi. For the cosine, it looks a little bit more like this, but the same thing. 0, pi, and 2 pi. And for the tangent, it'll be a little bit different. What's going to happen is you're going to have a shape that looks kind of like this from the origin, going up to infinity along the side of what is called an asymptote. You don't really need to remember the name of it. This would be the y-axis. And then over here, down to infinity and up again. And what happens is if you go forward, left or right, what you end up is a shape that looks a little bit like this over and over. Each time along the asymptotes heading toward positive or negative infinity, depending on whether or not it's on the top or the bottom half of the x-axis. And the period here goes from 0 at the origin to pi over 2 at the asymptote to just pi. That is the second time you're crossing the x-axis. This is a little bit different, but same idea. Now let's take a look at the transformations you can do. Like I said, this actually isn't that bad. What happens is the period is going to be transformed by the insertion of some constant a, say, before x uh, on the original sine of x function. So this is the original graph. This is what sine of x tends to look like, so or always looks like. This is sine of x. Uh, and if you have sine of 3x, for example, if we plug in a 3 in place of a, what happens is the period is going to decrease by 1 over a. So in this case, the period here, when it first crosses the x-axis, it's pi. Here it's going to be pi over a, and we just said a is 3, so it's going to be pi over 3. And 2 pi over 3. That's all that you need to know. The period will decrease by 1 over a when a is inserted here. Same thing for cosine. You have pi and 2 pi here, and we do, whoops, this should say cosine, not sine. So cosine of ax, so if we have cosine of 4x, that's going to be 1 over a, pi over 4, right? And 2 pi over 4, which is the same as pi over 2. The tangent is actually going to be a little bit different. It actually won't decrease. What's going to happen here is it's going to increase. Sorry about the slide here, but you get the idea. What happens is the tangent of x here is, if when you add an a here, what you're gonna have is for the, oh, never mind, never mind. The reason it's increasing is because this is pi over 2. It's the exact same thing. So it's going to decrease by 1 over a. And the reason it's increasing is because here it says tangent of x over 2. So what we're doing is we're decreasing it by a half. So if we're decreasing it by a half, it's going to increase from pi over 2 to pi, because pi times 1/2, or sorry, if you're going to decrease it by 1/2, that's the same as increasing it by 2. So pi over 2 gives you pi. Pi gives you 2 pi. Okay, that makes a lot more sense. If we look at the amplitude transformations now, what's going on? So amplitude just means the when you look at a regular sine function, it's oscillating over and over. It's oscillating between 1 and -1. And that range from -1 to 1 is what we call the amplitude of a regular sine function. When we want to change that, we multiply a constant value at the beginning of the function. So for example, instead of sine of x, we have a times sine of x, or in this case, 3 times sine of x. And the amplitude will simply increase by that value a. So here we have 0, 0, pi, and 2 pi, and that's going to stay the same. So it's not changing like in the previous example. Here we had 1 and -1, and the amplitude is what's going to change. The 1 is now going to be 3, and the -1 is now going to be -3. And that's how you know that the amplitude has been changed, and you know that you're going to need to have a constant value of 3 at the beginning, because you multiply 1 times 3, and that's what made that change. So let's go ahead and look at the same thing here. So the cosine of x, if we multiply it times a here, if we do 4, instead of going from 1 to -1, it's going from 4 to -4, so that's okay. And the tangent of x here, the amplitude is going to increase by a, and that's a little bit harder to see. So what happens is, for example, look at this. When the graph here is at 2, right, this function is moving up so much faster. The amplitude is increasing so much that it's there when you're actually getting to like about 1. And the reason is because we're multiplying this by 1/2. So when you multiply the tangent by, if you're amplifying the graph by 1/2 rather than 2 or 3 or 4, you're just gonna do the exact same thing we did before. Here we went from 1 to 3, we multiply by 3, 1 to 4, we multiply by 4, and now we're gonna go from 2 to 1, we multiply by 1/2, 4 to 2, we multiply by 1/2, or 6 to 3, we multiply by 1/2. So that's all you need to know. And it actually makes answering questions like this that could look really complicated at the beginning really easy. So let's go ahead and try this one together. The above graph represents a function. It's actually the below graph, but um, let's see. So this was the shape of a cosine graph, not a sine graph or not a tangent graph. So we can go ahead and get rid of anything that's not cosine. The answer is going to have to be around here somewhere. We also know that it has a period, sorry, an amplitude of 3, and that it's supposed to have one from, -1 to 1, not from -3 to 3. So what happened was the amplitude was changed, so it had to have had a 3 multiplied by it, so that can't be the right answer. And we also know that the period here, it usually goes to pi and to 2 pi, and instead we have pi over 2 and just pi. So it looks like these were divided by 2 so that a constant value must have been put inside the parentheses here before the x. So this has to be the right answer. It's not divided by 3, it's divided by 2. So we can cross that answer choice out there too. And that's all that you need to know for this sort of problem. The last thing that you need to know, and like I said earlier, this is a lot less important. It comes up very infrequently, um, but it may show up, so be sure to know it, are these formulas here, the law of sines and law of cosines. And this is great because it lets you solve for angles or sides of a triangle when you don't have a right triangle. So just so you know, for example, when you label, say, we're going to label this as angle A, the opposite side is what we're going to label side measurement A. And that's how you're going to be able to use these formulas. So imagine a triangle that works this way this time. Don't think of the Pythagorean theorem where A and B were legs and C was a hypotenuse. In this case, that's not going to apply anymore. C, there is no hypotenuse. This isn't a right triangle. C is just going to be the side opposite to where angle C is. So side measurement here will be the same as C. That's the notation that we're using this time around. So knowing that notation now, we can know that these formulas are going to work every time. So A, so this side over the sine of A is going to equal B, so side opposite B, over the sine of B, which is going to equal C over the sine of C. And that works every time, and it can help you solve for the side lengths or the angles of a triangle that's not a right triangle. This works the exact same way for the law of cosines, and this is really cool. So we know that, say, we want to know what the cosine of A is. Well, we know A squared. A is going to be opposite to, whoops, sorry, I'm not going to square that. The angle A, this value squared is going to equal B squared plus C squared minus 2 times B times C times the cosine of A. And then you can solve for it. So let's go ahead and look at an example of the law of cosines. So in the triangle below, the cosine of omega is equal to what? Well, we're looking for the cosine, so and this is in a right triangle. At least we have no reason to assume that this is a right triangle, so it's most likely not. And we have a cosine, so we know we can use the law of cosines to solve for the value of cosine of w because we have side lengths for every side given. So this is great. What we can do now then is say, well, the side opposite to omega is now what we're going to call side omega. Why not? Or A or whatever else we want to call it. It's omega. We're going to say h squared, right, equals b squared plus, or omega squared is going to equal b squared plus c squared. I don't know which is b or c. Let's just pick random ones. 7 squared plus 4 squared, right? Minus 2 times b times c, right? Times the cosine of omega. So minus 2 times 4 times 7 times the cosine of omega. So what we can do now is, well, let's subtract this over to this side. And we're going to end up with 7 squared plus 4 squared minus 8 squared. And let's add the other side over here. So we're going to end up with 2 times 4 times 6 times the cosine of omega over here. And what we can do is we can subtract the 2 times 4 times 6 from both sides and end up with this in the denominator, and I'm just going to solve for it because I'm sick of moving over 2 times 4 times 6. This is 12 times 4, which is um, 12 times 4, it's uh, 56. Wow, okay, yeah, that's going to be 56. And cosine of omega, then we're saying, is 7 squared plus 4 squared minus 8 squared. So we're going to have here 49 plus 16 minus 64. So 49 plus 16 is going to give me 65 minus 64. That's going to be 1. And we already have 56 in the denominator. This is the answer choice. So that's how these work. Now, I have already covered all of the formulas you'll ever need to score, the highest that you can on the trigonometry section. What you need to do is get some practice doing this kind of stuff on your own, and that's what the testive geometry and trig section is for. These are going to be interspersed along with the plane geometry problems, and you're going to see more and more as you advance to the higher levels on the geometry and trig section. But we have that available for you to practice and to increase your score as much as you can on the site. So I'm not going to say good luck. I'm going to say good fortune. You're going to be rewarded by rewarded for your efforts, as this fortune cookie says. This is a great fortune. Keep that in mind, and you're going to be great for this test. Good luck, everybody.